So, our purpose, so we said, is to learn how to compute areas and their function fx over an interval AB. So we saw approximation. We saw the approximation ways, methods using Riemann's, Riemann's sum. We algebraic operations, we can use them if we know some calculations. Okay, if we know fundamental basic area and we want to deduce others, we saw comparison. Okay, with two areas, with two functions, and we deduce the comparison on areas. There is something we didn't see, which was natural from the beginning, the term of area. We can use geometry, but this also has its geometry. It has its limitation because it depends on if we have simple geometry. So okay, so let's do an example that you should be able to do. So what about this area? Compute this area 1 over 0 to 1 of square root of 1 minus x2. So as you see, your function f here is square root of 1 minus x2. So even if you try to use Riemann's sums, it will not work. Algebraic operation, we don't have something known. Comparison, maybe, but yes, maybe we can have a comparison, but let's try you use geometry. Geometry, that means I need to identify my curve. Okay, so the curve, so here is my curve, is y square root of 1 minus x2. What is the set of points described by this curve? So we can identify it. So if you take both sides to power 2, we have y2 is 1 minus x2. Keep in mind that y is positive. Your y, the original y is positive, so keep the information here. Plus your x is between minus 1 and 1, because the square root here, the quantity must be positive. Okay, so now the second step, look what we obtain here. We will obtain, if you move the x2 to the other side, you will get x2 plus y2 equal 1, with y positive and x between minus 1 and 1. So from here, we see that the equation x2 plus y2 is a circle, a unit circle. This one is the unit circle. Okay, so then the condition y positive means that we need just the upper half of the circle. Okay, so here is, if you want to graph it, your unit circle, here it is. So let's say I have, okay, I have my unit circle. So it's not that accurate, but it's okay. So here I have the half part. So this is my upper half, y equals square root. The lower half has the equation y equal minus square root 1 minus x2. So I am looking for the area from here. There is minus 1 to 1. Here is 0. I'm looking at the area over the interval 0, 1 under the curve. So that is this region. So let's change the color, take the green color. So I need to do this one to compute this area. Okay. So this is this area. Then here is my number I want to compute. Okay. I know it's 1 over 4, it's equal to 1 over 4, okay, 1 over 4 pi r square. R square is 1 square, okay. The area of the total disk is pi r square, so we will have the value, exact value, pi over 4. Okay, so we can use geometry in very specific situation where we can have simple shapes that we know already how to compute areas. Okay, now today we will see a powerful tool that is called um, the fundamental theorem. Here is what it says: fundamental. So the fundamental theorem will allow us to compute so yes, will allow us to compute areas knowing what an antiderivative of the function. Here is the theorem, what it says. Here is the theorem. Theorem says if we have a continuous function f is, let's say, c0 over the interval eb, okay, then the area, the exact area of f over the interval eb under the curve y equal fx is exactly capital Fb minus capital Fe, where f prime x is fx. That is capital F is non-antiderivative, okay? That is f is just non-antiderivative of f. So this is what the theorem says. As long as we know an antiderivative of f, we can have exactly the area needed, okay? And the objective, our objective later, is to learn how to find those antiderivatives depending on the function, being a power, polynomial, fractions, trigonometric, or new functions like logarithmic function or hyperbolic functions. So this is our yes, our purpose. Okay, so let's yeah, the idea is, so let's first do a simple example. Okay, simple example. For example, here for the previous example we started with, we have a function. For a moment we don't know how to compute an antiderivative of square root 1 minus x2, so we won't be able to do it. Answer to the question, use the fundamental theorem now. For a moment we don't know, but we can we know an antiderivative for power functions. So for example, if I need to compute the area under the function x4, so power, from over the interval -2 to 1, it's easy. I know the antiderivative. So yes, I need to tell you something else here. Use another notation. You can use the notation, the following notation, okay? Okay, so we have another notation is to say it's fx sometimes fx, and you put a to b, okay, like that, endpoints. So here for my situation here, I can say that my area will be, so x5 over 5, be I to take it minus, or x equal -2 to x equal 1, then make the difference. So substitute first the upper bound, so we will have 1 power 5 over 5 minus -2 power 5 over 5. Okay, so I give you the value. So I didn't do the calculation. Okay, so 4 times 4, 16 times -2, 32, minus 32, and minus plus 32, 133 over 5. So here is you see how it is easy. And this is the exact value. That means the limit of Riemann we were looking for. Okay. So, yes. Yes. So I would like to give you an idea of the proof. It is interesting to know it, to have an idea how it is proved. So I will give you just the outline of the proof. So let's see how it works. So we want to show this equality. This difference is equal to the area exactly. From the area, we know just the definition of Riemann using the Riemann sums. So let's start writing FB. minus fe. I need, my idea is to connect it to a Riemann sum, so I will divide my interval eb on n sub intervals eb, okay, up to xn, and this is x0, etc. as usual. So it will be, and then I will write fxn minus f xn minus fx0, okay. Then what I will do, I will separate, add one term and subtract a term and add at the same term, so that I don't modify my equality. So I will have xn minus 1 plus f xn minus 1 minus f xn minus 2, etc. Okay, up to f, so I will have here x1 and minus fx0. Okay, and if you look, and then what it's good to remark, to regroup those terms like that, to regroup them 2 by 2 like that. Okay, so so finally my sum, I can write it as the sum from I to 1 to n of this difference of xi minus f xi minus 1. So this is how it is. Now I will work on this difference. So I will add one line. Let's keep the sum here. So I will use the mean value theorem. Mean value theorem says the difference taken by the function m for two values is equal to an intermediate point value. Let's call it this one, okay, times the difference xi minus xi minus 1. Okay, so this is the mean value theorem applied by f of to f of f on the interval xi minus 1 xi. So the xi star belongs to this interval. Okay, this is what it says theorem. But now we know that f prime, what we know that f prime is equal to fx. Okay, so we have this equality. Don't forget this one. So I will substitute. I will get then sum f at xi star times the delta xi we called. But this is exactly Riemann sum. We said that the Riemann sum, the limit doesn't depend. Okay, so if you take the limit, okay, so this is, yes, so this limit exists, so it is equal to the limit. Okay, it's equal to also to the limit, so I don't have to write it here because this quantity exists, it's constant, so the limit exists and is equal to, which is exactly here our indefinite integral we wanted to compute. Okay, so this is the idea, which is very beautiful proof. Okay, so let's do one more example just to practice. So the more you practice, of course, you will develop, you will learn better, know how to do, explore different situations, because each case has its own difficulty. Okay, for example, if I need to compute, for example, let's look at this one. Yes, for example, the integral, definite integral of 1 to 2 of 2t squared plus t, yes, t2, then square root t minus 1 over t squared dt. Okay, so I need to find the definite. So the idea is to apply the fundamental theorem, find an antiderivative, but as I see here, combination of functions, a ratio, fraction with square root. So I'm not sure I know exactly the antiderivative, but maybe I know it. I need to work on find an antiderivative, work on my function, try to write it differently maybe. Okay, so if you write it differently, let's do. So I can see I can divide by t squared, simplify and get something like that. Okay, and now I see I can use operations one operation on integrals. Okay, I can do that. Okay, and then find the antiderivative for each of the functions. So I have 2t to take between 1 and 2. This one, it's power function, so it's t 1 over 2 plus 1 over 1 over 2 plus 1 to take it back. Minus this one is t minus 2 power function also. You see, still we are limited with our how to find antiderivatives. That's why we need to know how to find antiderivatives. Okay, and we have the exact value. Another situation, for example, that involves, for example, absolute value. Another example. Let's do another one. What about the integral from 0 to 2 of 2x minus 1 absolute value dx? So this time I need here, I have, yes, I need to work on my function, on my integrals. I need to avoid the absolute value, but this can be made if we eliminate this depending. So we need to know when we can eliminate these absolute values. Okay, so here it is. We can do it because we know that it will be 2x minus 1 if my x is greater than 1 over 2, and the opposite of this quantity if x is less than 1 over 2. Okay, so that's why then, since I'm working from 0 to 2 and 1 over 2 is between, so I need to separate my integral. Okay, I need to separate it and write it differently. Okay, so if I'll call it g here, then g will be the integral I will compute from 0 to 1 over 2. Then from 0 to 1 I am here, so my function is minus 2x minus 1 dx, plus then the integral from 1 over 2 to 2 of the function 2x minus 1 dx. Okay, and here it's easy to find an antiderivative. We know it. It's minus x2 minus x to take it between 0 and 1 over 2 plus x2 minus x to take it between 1 over 2 to 2. Okay, so this is how we yes, and you need to practice, of course, so that you get all different techniques, you develop more tools. Okay.